coming to the problems on open circuit test and short circuit test of single phase transformer. So here a 5 kVA, the S value is 5 kVA, 500 volts by 250 volts, 50 Hz single phase transformer. This is HP and this one is LV. Gave the following readings. Open circuit test is conducted for this problem on HV side. LV side terminals are open circuited and the LV side terminals are open circuited, but short circuit test is a low voltage terminals are short circuited. So both OC test and SC test of a single phase transformer is connected on high voltage side. So determine the efficiency on full load 0.8 power factor lagging, the voltage regulation on full load 0.8 leading power factor, the efficiency on 60% of the full load, that means X value is 0.6, 0.8 leading power factor. Draw the equivalent circuit, refer to primary and insert all values in it. So coming to the solution of this problem. So HV side, the no load parameters are, so V is equal to 500 volts and the no load current is given as 1 ampere and the W0 is equal to 500 watts. Sorry, W0 is 500 or 50, yes, 50 watts. The W0 is 50 watts. Here W0 is equal to V into I0 cos phi 0. From this you can calculate the power factor. Cos phi 0 is equal to W0 divided by V into I0. So W0 is 50 divided by V is 500 into 1. That should be equal to the power factor under no load condition is 0.1 lagging. It's a 0.1 lagging. So after that, should calculate the magnetizing component of current and the wattful component of current. The wattful component of current is I0 cos phi 0. The I0 value is 1. The power factor is 0.1. The IW is 0.1 amperes. Im is equal to I0 sin phi 0. So 1 into sin phi 0. So from this you can calculate the phi 0 angle. The angle is 84.26 degrees. So 1 into sine of 84.26. Then I got it as 0.994 amperes. So we are calculating the Im and Iw. What is the no load equivalent circuit? From the open circuit test, we already known that we should calculate the equivalent circuit of shunt branch parameters, and this is Iw, I mu or Im, so I0, and the supply voltage is V. R0 is equal to V divided by Iw. R0 is equal to V divided by 500 divided by 0.1. That should be equal to 500 divided by 0.1, 5000 ohms. Similarly, you can calculate X0 is equal to V divided by I mu or Im. V is 500 and Im is 0.994. 500 divided by 0.94, that should be equal to 502.519 ohms. So we have calculated the no load branch parameters from the short circuit test. Yes, from the SC test you have to collect the data. So 25 volts 10 amperes and 60 watts. Check that is it correct rated current or not. I2 is equal to, or I1 is equal to the current at high voltage side should be equal to kVA rating is 5000, so 5 kVA divided by 500. Yes, this is a rated current on HV side. So all the parameters are HV side. So this is VSC is 25 volts and ISC is equal to 10 amperes and WSC is equal to 60 watts. WSC is equal to ISC square into, so RHV. I am representing in HV in order to avoid the confusion. Or R01, you can write it R01 also. So R01, from this R01 is equal to 60 divided by ISC square is 10 square, that should be equal to 0.6 ohms, and ZSC is equal to, or Z01 is equal to 25 divided by 10 VSC divided by ISC, so that should be equal to 2.5 ohms. So from this we can calculate X01 is equal to under root of Z01 square minus R01 square. So Z01 is under root of 2.5 whole square minus 0.6 whole square. Then I will get the X01 is equal to 2.4269 ohms. 2.4269 ohms, that is called the X01. So we have calculated R01 and X01 also. So this is a V2, E2. So we can find voltage regulation also. But first question is efficiency on full load. 0.8 power factor lagging. So efficiency at X fraction of load is equal to X times of kVA cos phi 2 divided by X times of kVA cos phi 2 plus iron losses plus full load copper loss. So here the X value is 1 because it is a under full load condition. So efficiency at full load is equal to, so 5 kVA 5 into 10 to the power of 3 into 0.8 divided by 5 into 10 to the power of 3 into 0.8 plus iron losses is obtained from open circuit test, that is 50, and the copper losses is 60, multiplied with 100, then you will get the percentage efficiency. The percentage efficiency value I am getting as 97.32%. This is called the full load efficiency. Coming to the regulation at full load. So the second bit is asking an regulation on full load. So regulation on full load at cos phi is equal to 0.8 leading. Percentage regulation is equal to I1 into R01 cos phi 2 plus or minus I1 into X01 sin phi 2 divided by E1 divided by E1. So this test, open circuit test and short circuit test, both are conducted at high voltage side. I1 is 10 amperes and R01 is calculated from the short circuit test divided by E1. What is the E1 value? Is 500 and the power factor is 0.8. So leading power factor, here plus is for lagging power factor and minus is for leading power factor. So minus 10 into the x0 one, we are getting 2.4269 divided by 500. If cos phi 2 is 0.8 and the sin phi 2 is 0.6, remember, or vice versa. If cos phi 2 is 0.6, sin phi 2 is 0.8, so multiply with 100, then you will get the percentage regulation as minus 1.95 percentage. This is a 0.8 leading power factor. And the finally is the third one is for 60 percentage of the load, 60 percentage of full load, the x value is 0.6 and the power factor which is given is 0.8 leading or lagging, which will not affect the efficiency of transformer. So direct substitution efficiency at 0.6 is equal to 0.6 into kVA is 5 into 10 to the power of 3 into 0.8 divided by 0.6 into 5 into 10 to the power of 3 into 0.8 plus iron losses. So what are the iron losses is 50, that is constant, plus x square times of full load copper loss. It means 0.6 volts square into 0.6 volts square into the full load copper losses what you are obtained in 60 and multiplied with 100, then I am getting as 97.103 percentage efficiency at 60 percentage of the full load, 60% of the full load. And what is a finalized equivalent circuit now? All the parameters are referred to HV. So this is R01, X01, and the no load branch parameters are also referred to HV side only, because both the open circuit test and short circuit test are conducted on HV side. So substitute the values. The R01 value is 0.6 ohms. R01 value is 0.6 ohms. X01 is 2.2462. Sorry, 2.4269. 2.4269 ohms. And the R0 I obtained as 5000 ohms. X0 is 502.52 ohms. And here high voltage, that is 500 volts. Okay, this is the equivalent circuit of single phase transformer when referred to HV side. Okay, so this problem is covered most of the topics. If you remember, it is very easy. The first step is asking to calculate the efficiency and full load at 0.8 power factor lag. So before that, we calculated open circuit test. From the open circuit test, we calculated no load losses and shunt branch parameters, and from the short circuit test, we have calculated the copper losses and series branch parameters. And if we know the losses, we can find the efficiency. And after that, from the short circuit test, remember this is very important. From the short circuit test, we can calculate voltage regulation. After that, the third bit is efficiency is calculated on 60% of the full load, 0.8 leading power factor. Once again, leading or lagging, which will not affect the efficiency, you will get the same. And the final one is rather equivalent circuit referred to primary and insert all the values in it. So this is the equivalent circuit of a single phase transformer for this problem. So coming to the next problem, the open circuit and short circuit test on a 10 kVA 125 by 250 volts 50 Hz single phase transformer gave the following results. From the open circuit test is conducted on LV side. So open circuit test is conducted on LV side and the HV side terminals are open circuited, and short circuit test is conducted on HV side. So that means low voltage terminals are short circuited. So first of all, copper losses on full load. See, from this short circuit test data, VSC is 15 volts and ISC is 30 amperes and the WSC is equal to 100 watts. Check that this 30 amperes is the rated current or not. So 10 kVA 125 divided by 250 volts, and this is high voltage, this is low voltage, and this test is conducted on high voltage side. So you should calculate the current on high voltage side. So current on HV side, 10 into 10 to the power of 3 divided by 250, that should be equal to 40 amperes. That should be equal to 40 amperes. But in the problem is given as 30 amperes only. Copper losses is directly proportional to I square. The copper losses 2 divided by copper loss 1 is equal to I2 divided by I1 whole square. So we have to calculate for 40 amperes 40 by 30 whole square, and this copper loss 2 is copper loss at full load. Is equal to 40 by 30 whole square into copper loss 1 is that is at 30 amperes is given, the test is 100. So finally copper loss at full load or 40 amperes should be equal to 177.78 watts. Coming to the second case, on full load, so calculate the efficiency at 0.8 power factor. So percentage efficiency is equal to, on full load X value is 1, full load X value is 1, kVA cos phi 2 by kVA cos phi 2 plus iron losses plus full load copper losses. Full load copper losses. The kVA is 250 or E2 is 250 and the current is 40 into 0.8. So we know that E2 I2 is also kVA of transformer. So 250 into 40 into 0.8. The iron losses which were obtained from the open circuit test, that is 50, and the copper losses is calculated at full load 177.8 multiplied with 100. Multiplied with 100. Then I got it as 97.23%. This is efficiency at full load. So 97.23. So he is asking at half load also. The X value is 1 by 2. The current I2 now will becomes I2 divided by 2. I half load is I2 by 2. Substitute here, efficiency at half load is equal to 1 by 2 times of 250 into 1 by 2 times of 250 volts into 40 into 0.8 divided by 1 by 2 times of 250 into 40 into 0.8 plus iron losses won't change, but the copper losses will be changed 1 by 4 times, because x square copper losses, x is 1 by 2, x square is 1 by 4th times, the copper losses are reduced to 1 by 4 times 177.78 multiplied with 100, then I will get the 97.69 percentage. This is the efficiency at half load is 97.69 percentage. The second question is also calculated, and means copper loss at full load calculated, full load efficiency is calculated, off load efficiency is also calculated. The third one is regulation at full load. So regulation at full load we have to calculate it. So percentage regulation is equal to, so before that, from the short circuit test data, Vs is equal to 15, ISC is 30, so ZSC you can calculate 15 divided by 30, that should be equal to 1 by 2 is 0.5 ohms. So ISC is equal to WSC is equal to ISC square into R01. So WSC by R01. From this we can calculate R01 is equal to WSC by ISC square. What is the WSC value? It is 10 divided by 30 whole square, 0.111 ohms. R01 is calculated, and Z01 is also calculated. From this we can calculate X01 is equal to Z01 square minus R01 square. So finally I got it as 0.4875 ohms. So it is a percentage regulation formula. So I1 R01 cos phi 2 plus or minus I2 X01 sin phi 2 divided by E2 into 100, sorry, E1 into 100. What is I1? The I1 which is calculated is a full load current is 40, R01 is 0.111, this is 0.9. is asking at leading power factor. For a leading power factor minus, you should take it 40 into 0.4875 into 0.4358 divided by 250 into 100. So finally I got it as minus 1.8015 percentage. So now the percentage regulation formula or value at full load is equal to minus 1.8015 percentage. So in this problem, compared to the previous problem, it is a somewhat twisty problem. This data, short circuit data, y is given means this short circuit data is to calculate the series branch parameters. After that you will check that is it a rated current or not. If it is not a rated current, you should find out the full load copper losses. In the problem, if he mentioned that calculate the efficiency, then we need full load copper losses. If you find out the full load copper losses from the short circuit test and also iron losses from open circuit test, we can calculate the efficiency. From the short circuit test data, we should calculate the percentage regulation.